Okay. So, we start with community uh, structure identification. We continue the class. What we have seen is we were talking about random betweenness. Okay. So, when we think of random betweenness, let us see that we take the adjacency matrix A. Okay. So, what does the adjacency matrix gives? The link from I to j. Okay. So, all the links from any node I to any node j. Now, what I want? I think there is a random walker going, okay, and the random walker starts from j. Okay. Random walker starts from j. What is the probability that it will be at I after one step? So, my question is simple, that I have a random walker which starts from j and I want to know what is the probability that the random walker will reach I after one step. Okay. So, that actually gives us the transition matrix, okay, which we defined as Mij. So, what will be the probability? It is, if it is connected, then only there is a chance. If it is connected, then only there is a chance. And how much chance? So, if I have this as I and this as j, and j has k j links. Okay. So, the chance that the probability that the random walker will reach here is A I j by k j. Okay. So, that is why you get the transition matrix, which I again write is A I j by k j. Okay. Clear? So, taking this into consideration, what we can write is M is equal to A D inverse, okay, where D is a diagonal matrix, D I I is equal to K I. No problem. So, the same thing I am writing in a diagonal matrix. So, now what is the problem? That I am given a source, I am given a destination and I want to find the random walk betweenness of a edge for this particular source destination pair. Okay. So, this is what I am trying to do. This is the problem which we are attempting, that given a source and given a destination, I want to find out the number of times a particular edge will be crossed. This is what I am trying to find, and what I have defined, that I will if it is u and v. Okay. So, it will be crossed many times by u and v, from u to v, and also many times from v to u, and I just say t is equal to, okay. Okay. Now, one problem if I with the destination pair. What is the problem with the destination pair with this random matrix is that, okay, first let us think when we get the transition matrix. So, what happens is, what will this be, m to the power n? What does this matrix represent? Yeah, it again will show the probability okay, that you reach some I after n steps. Okay. So, this is clear. Okay. Now, can you tell me if I have a source destination pair, what is problem with M n? There is a problem if I take random one betweenness and if I do m to the power n, there will be some undesirable paths which has to be taken care. See, there will be some paths where you have reached the destination pair at time less than n. Okay, you have reached the destination pair at time less than n. Okay. And then you have again gone back to others and traveling. Okay. So, what is happening? You are also considering paths where you have already reached D and then again going back and looping. Okay. This is clear. So, we cannot consider that once it has reached, it has reached. Okay. Okay. So, you know there is a this simple class 5 problem that there is a monkey which goes up 3 steps and comes down 2 steps at each minute. How many minutes will it take to reach 20 meters or 20 steps? Okay. Or how many minutes will it take to reach 3 steps? It is 1 minute, it is not 3 minutes. So, it is the same thing we have to consider here. Okay. So, then what we do, the simple solution is from M you produce a M D, where D is removed. Okay. The row D is removed. Okay. So, simply reaching D is reaching any step and then transition to D. Okay. So, you think in that way and you remove D. Okay. So, now you have the matrix and then m to the power D plus m to the power D square plus m to the power D cube. In this way m to the power D n D infinity. What does this give?
In 1 or 2 or 3.
Yeah, means it's a asymptotic limit that if you go on for infinity, what will be the transition probability? If you go on for infinity, what will be the transition probability? Okay. And so, if I take any, so this is a matrix, if I take any cell V s, what does this show? If I take any cell V s of this matrix, what does this show? So, take this matrix, okay. Take this matrix where okay, I should draw M. So, M can be A11 by K1, A12 by K1, A22 by K2, A23 A21 by K2, A22 by K2, a small M matrix. Okay. So, M12 is basically what? What is M12? If you have started from 2, what is the probability that you reach 1? Or if you started from 1, what is the probability you have reached 2? Which one? I think I wrote I made a mistake. Sorry. So, what is M12? What is M12? If you have started from 2, what is the probability that you have reached 1? In one step. Yeah, obviously, if you have started from 2, what is the probability that you have reached 1 in one step? Okay, no problem. So, tell me what is this m d infinity V s? If you started from S, what is the probability that you are at V after infinite steps? Okay. After infinite steps. Okay, no problem. Okay, so now this can be simply written as, this is a simple expression. What can it be written as? 1 minus m d minus 1. This is an infinite series. So, infinite series can be written like that, no problem. Okay. So, now again I try to write that this 1 minus m d minus 1 V s gives you that you will be at node V. Okay. Now, consider that this is V and this is U, okay, and this is the edge V U.
It should be MD divided by 1.
Huh?
It should be MD divided by 1 minus MD, because you are using MD should be common. MD into
MD should be here. Okay. Okay. Means actually it is good you have said it, but we can think it like this, m d to the power 0 plus m to the power 1, means after 0 steps, after 1 step, after 2 steps. So, then this becomes 1 minus m d. Okay. Clear? Thank you. So, if you have V to U, so what will that be? So, now I want to see, I know that asymptotically what is the probability that I will reside at V. Okay. This is clear, and there is a edge V U. So, what is the probability that in the next step the random walker will pass from V to U? 1 by degree of V. Okay. So, now minus, so random walk betweenness you get is minus 1 minus m d, again infinity U s by k u, and you take the mod whichever is more. So, it is so elegant, if you think it is extremely elegant that you have a complete random process, but you can again capture it through linear algebra. Okay. So, accordingly you can it can be shown that these things will be needed. You have to calculate this matrix, okay, and from this matrix you can do this. Okay. So, this you get random walk betweenness for a particular pair. Okay. You get random walk betweenness for a particular pair. okay, and then you can do it for all pairs, all SD, and accordingly you get the random walk betweenness. The problem is, what was the complexity of the previous algorithm, of the shortest path algorithm? It was m square n, I think, and here it goes one magnitude higher. So, it is actually, I will not do the complexity part, but it is order m n square. Okay. So, complexity of community formation using random walk betweenness. Okay. Okay. So, the basic concept is clear. Any question? Okay. The next point which we try to identify is okay. Before this, we tell another very simple algorithm of community formation. So, Radich's algorithm, this is a fast algorithm, and perhaps this is most used. Okay. So, the idea is very simple. The idea is, if you have a node, okay, you want to see with the, if this edge, whether community edge or not. Okay. So, this is the question which you are asking. Given an edge, whether this is the question you are continuously asking, and previously what we have done? We have seen that whether this edge has high betweenness, some sort of high betweenness or not, and we have told that high betweenness means that it is a community bridging edge, it is a bridge edge. So, it is bridging communities. So, remove them. Now, I tell that if think this way, that given this edge, there is a community out here. Okay. If there is a community out here, what will happen locally? There is some nodes here, some nodes here, okay, and there will be there has to be some links, there has to be some, there will be more links also perhaps, but the number of links should be less. So, this is a cut concept, that the cut should be less. Okay. So, that is what we are thinking. Now, in this Radich's algorithm, the assumption is, if this node is part of many triangles. So, consider this is a triangle. If this is a part of a triangle, then this node should be here or here. It can be either in this or in this. In both cases, what is happening? There is another bridge other than this bridge. If this node is here, then there is this bridge. However, if you have a separate community, okay, then this is a second bridge you have. Okay. So, in both cases, what is happening? That the division between communities are having more than one bridge. The division between community is having more than one bridge, which is bad. It should not be. It should be that number of bridges should be minimum. We do not know what the term minimum means, but it should be minimum. Okay. Clear? So, then what we can say that what do we think of clustering? What is clustering basically? What is this triangle formation? This is basically clustering coefficient which we see. We have seen. Anyway, that is not needed. I have a I j. Okay. I have a edge I j. Okay. So, I define a term j I j, which means number of triangles which are formed and I j is a part of. Okay. Which a form can be a number of for which I j is a part of. Okay. Number of triangles for which I j is a part of. Okay. So, how can you tell me what is the maximum number of triangles I j can be part?
ij is
Yeah, I j. Yeah, this is I, this is j. So, this is E I j. So, the maximum number of no, the maximum number of triangles which no. I think degree is a good concept, but tell me more precisely. No, nothing. It is degree of I and degree of j, but what relation? Min of ki and kj. Because you think why it should be min? Because anyway these two nodes has to always participate. Okay. And for how many can it participate?
then the least number of degree.
No, it is not also minimum. Minus 1, because 1 is already here. Because number of triangles can be min of ki, kj minus 1. Huh? Yeah, that is the maximum number of triangles that can be formed. That is what I am telling, is the maximum number of triangles that can be formed. Okay? And if 0 triangle is formed, then this becomes 0. Okay. And so, for that you can normalize and give a 1. Okay. That if 0 triangles is formed, it is just 1 of this. Okay. So, this gives you a we call it a community coefficient. Okay. We can call it community coefficient. Agreed? In denominator. In the numerator, I have added 1 because it can be part of 0 cycles. It can be part of 0 cycles. Now, think, okay. So, why have I added 1? That is the question. So, there can be situations I am part of 0 cycles. 0 triangles rather, I am part of 0 triangles. So, now in one case I have 10,000 nodes. Okay. In one case I have 10,000 nodes and I am part of 0 cycles, and in another case I am part, which means I am not part of 10,000, means the nodes each has, say this has 1000 and this has 1000 links, and in another case the node, this node has 2 links and this node also has 2 links, or 2 or 5, let us say 5 links. Okay. So, now what will happen? See this measure, in both case if I do not have 1, in both case it becomes 0. Okay. But in this case this C I j becomes 1 by 1 by yeah, and this case it becomes 1 by 4. And so, which is a better community edge? 1 by 1, sorry, 1 by 1, 2 minus, no, okay. Anyway, so this is excess degree, think this is excess degree, then I should write this is 100 and this is 1 by 2. Okay. Just this is excess degree. Clear? Any question? Okay. So, great. So, so which should be removed? Which is a more community bridging edge? This one is a better community bridging edge? Huh? Yeah. Obviously, this one is a better community bridging edge. Okay. So, worst case what happens is you have 2 nodes and this is the link. Okay. Then down becomes 0, so the value becomes infinity. Down becomes 0, so the value becomes infinite. You can understand, if I have a node with just 2 degrees, you cannot really say this is a community edge. Okay. So, this is a better community edge. So, now what is the algorithm? Algorithm is calculate for each edge community coefficient and go on removing the lowest, the edge with lowest value. Okay. Okay, you can take any shot at the what will be the complexity? This will be order m, okay, because calculating for each individual edge will be constant and there are m edges. No, you are just seeing this part, no. So, it is Ku and Kv. So, you have to check, means if I Ki Kj. So, you have to check whether for a particular Ki and Kj you have a common edge. You can think that Ki and Kj is small, then it is constant. Yeah, think for a particular edge. Okay, think for a particular edge. Think Ki, Kj. Okay. And so, how many you have to check? Mean of Ki and Kj, that is the maximum you can have, mean of Ki and Kj. So, what you do? You take a Ki, you take one and take one from here and see that whether there is a common edge, common node. It will become Ki into Kj, and I am assuming that Ki and Kj's are small. Okay. You think this is small, then it is constant. Okay. Okay. Great. So, once this is done, another concept is what we said, how do we define modularity? How do we define modularity?
The previous one, the M matrix we have defined, the previous method, how did you decide that what should be, which edge should be removed?
How did we?
Decided that which edge should be removed for community formation.
So, that was that which has the highest randomness betweenness. So, according to that you calculated the random walk betweenness of each node, and whichever has the highest has been removed. Okay. So, let us come to modularity. Okay. So, what we do in modularity? Modularity definition, there can be many definitions of modularity. Okay. There can be many definitions of modularity, but one important way you can think is what we saw in the associative coefficients, that you have say community 1, community 2, community 3, community 4 and you write it. So, the question which we were asking is, given a community form, means we have formed a community, okay, like we have broken up the network into 4 pieces, C1, C2, C4, 3, C4. Now, what is the question? How good it is? Okay, how good it is? Now, you can see the what is the how good it is can be defined as if the number of edges inside is more than the number of edges outside. Okay. And but there is a problem with this. The problem is the best community is the entire network. If I say then all the edges are inside, no edge outside. So, you cannot really take that as a. So, if I write that this is EII, E11, E12, E13, E14, okay, I can write E22, E33, E44. Okay. So, these are the number of edges which are inside the community, and this is the number of edges, this is the number of edges connecting the communities, between the communities. So, this will give A1, A2, A3, A4. Okay. Clear? So, now the simplest definition which we also have seen in associative coefficient, if you remember, is Q is summation of EII minus AI square. Means I hope this is A1, this is, since this is symmetric, this is also A1. So, what we know, A1 into A1 will be equal to EII when AI A1 square is equal to EII. When is it equal? My probability theory, when will be A1 square equal to EI? When P A when P A dot B becomes, I think we know this is independent event. It becomes, so this is a total random thing. If there is a random occurrence, then or independent occurrence, then we say P A dot B is equal to P A into B B. So, this into this will be equal to this. Okay, you remember this? So, higher this value, higher is, lower is its randomness. Okay. Higher value, means lower randomness. Okay, it is fine. So, this way you can define modularity of communities. So, this is what we say defining modularity of communities. Higher its value means you are getting better community, means the cut is better. That is what we are telling.
So this is value for the entire cut, C1, C2, C3, C4.
Yeah, it is a value for the entire thing. So, this is what we want, that given given a network, I have broken down the network and now I want to say how good has been this my algorithm. And there is one way of seeing that we told in last class, that is looking at the data. If I see that all vowels have gone in one part, all consonants have gone in one part, it is good from my a priori knowledge. And now I do not have any a priori knowledge, I just want to define a blind metric or blind evaluation metric. So, this is what it is doing. Okay?
This one is for first community, for C1.
No, this is for entire thing, for all i's. This is giving modularity of community. It is means it's a network, entire network evaluation. No. It is not one single community, entire networks evaluation. That how EII, see no, PAB is equal to PA into PB, then EII is PA into B, probability that it has occurred in C1 and C1, means one edge is in C1, another edge is in C1, probability that some edge is in C1, means one edge is at least, means one edge is one node, edge has two nodes. What is this showing? That both end of the edge are in same community. Here what is it showing? That one end is at least in community 1, and this is also showing that the other end is at community 1. Yeah, it is sum of that row. No, why it will become? If EII is the entire value, then what is happening? This is becoming EII and this is becoming EII. Okay. Then EII minus EII squares. Okay. No, why negative? It is positive. EII is less than 1. So, it is becoming positive.
Should that be AI?
I wrote AI. Okay, I have written AI only. EII is the number of edges within a community. Okay. No, you can normalize it, it is not a big deal, you can normalize it.
If EI, I mean this value becomes 0,
Hmm.
then sum will be 0, and the value is 0, it means that it is a good community because all edges belongs to particular group.
If this value becomes 0, that means what? The edges all have come just randomly, there is no link. Means if think of this is node 1, this is node 2, okay, and node 1 and node 2 are in same community. Okay. Node 1 and node 2 are in same community. Now, the question is have they come by chance in the same community, or really you have designed something and done some modularity? By chance means what? By chance means this value will be equal to this value.
So, in this only diagonal elements are more than 0 and rest of the elements are 0, which means that we have 4 different components. So, it is a good community formation, but the value is 0, modularity.
Yeah, that is the question. So, what you are telling is you are thinking of a situation where this is the situation, everything else is 0. Are you thinking of such situation? Okay. So, first of all, what we assume is this cannot be the situation, because we assume is a connected graph. Okay. This immediately says that this is not a connected graph. Means that is, if it was not a connected graph, then you do not need this. The question again is that you need some edges, inter community edges. So, that is why you need some measure, so that this part gets minimized. I do not know what the term means minimized, but this part gets minimized, but there are some. Okay. So, next we go to the Kernighan-Lin algorithm. Okay. So, Kernighan-Lin algorithm, all of you know where is it is used? It is used in VLSI floor planning. So, it is a very popular algorithm in VLSI. So, see this. The point is partition a circuit in such a way that the number of connections among subsets is minimized. Okay. So, you partition it, because this may be in one chip, this may be in another chip, and those will be just interconnects, and I want to minimize the number of interconnects. Clear? So, let us think what is the algorithm about. That I have say 2n nodes. I want to divide it into n and n nodes, so that the partition becomes minimum. Okay. Clear? The cut becomes minimum. So, it has been shown. So, what is the difference between the other and here is that n and n are specified. So, the size of the community is specified. Okay. So, what has happened is size of the community, but it has been shown that this algorithm is NP complete. Okay. So, Kernighan-Lin is basically a heuristics. Okay. Kernighan-Lin is basically a heuristics. So, what is the heuristics about? So, you have one step where first you divide arbitrarily into 2 AM and BM. Okay. Means initially it is A0, B0, then you go on some iteration. I am showing a dynamic iteration point AM and BM. Now, this is say XM and this is YM. Through some mechanism, you identify a subset XM and a subset YM and interchange. Okay. So, it is a typical optimization type of problem. So, you try to minimize cost, okay, maximize benefit perhaps. Okay. With this exchange, you can say it in many ways that you minimize cost. So, this exchange minimize cost, some cost. Okay. Yeah. So, what is the cost? The cost of cut. Okay. Cost is cost of cut. Exchange of nodes. I first arbitrarily put some nodes A0 in one cut, another nodes, another set of nodes in another cut. Okay. Clear? Okay. So take an example, maybe that is better. And you go on, okay, the point is you go on exchanging and do exchange as long as you gain and stop as soon as you finish gaining. Okay. Okay. So, take this simple example. So, V2, V3, V6, V7, V1, V4, V5, V8. Okay. 2, 5, 1, 5, 1, 1, 1, 1, 3, 1, 1, 2. Okay. So, this is a very simple example. So, first cut is this way, say. Okay. Now, I want to first see the cost of each. So, cost of any node A, I tell it as dA, is external cost minus internal cost. Okay. Means number of connects it has externally and number of connects it has internally minus. Okay. Means because why I am doing the minus, the cost is I want to minimize cut. So, the cost is basically cut, and why I am doing minus internal cost? Why I am doing minus internal cost? Because if I swap it to other node, this internal cost will become the external cost. Okay. Clear? Okay.
So, you just want to minimize the number of edges. So, why not keep the cost 1?
No, I have taken the edges are weighted. That is why it is.
For a community, we just
No, here we taken the edges are weighted. Okay. Some has say 7 fan out, another has 100 fan out. So, some transistors have, so it is depending upon the functionality. So, you are generalizing it. You can always take everything as 1 and do it, it is not a big deal.
the ultimate result will not depend upon the internal rate. You have to just minimize the external.
Yeah, you have to just minimize the external device. Okay. So, clear? So if I think again dB is EA. Okay. Now, when I swap dA and dB, when I swap A and B, what happens? What is the cost? What is the gain? Sorry, I should be EBDB, sorry, it is EBDB. It will be dA plus dB. Anything else? Minus something twice, means you have to consider that within this external cost there may be a link between A and B. See, take 2 and 4, take 2 and 4. When you swap 2 and 4, this connection, this external connection of 2 still stays the external connection. The external connection from 2 to 4, we are swapping what? Swap say 2 and 4. Then external connection of 2 from 4, is it becoming an internal connection? It is not becoming an internal connection. So, the connection within this pair is still staying external. The connection within this pair is still staying external. Clear?
So what does this delta represent?
The gain, I want to see the gain. Delta is the gain. See, first forget 1, just 1. If I have taken this to here without swapping, if I have taken this to here, what would have happened? How much would I have gained? All internal links would have become external links and all external links would have become internal links. So, I would have gained dA, and I have taken this to there, then I gain dB. So, dA plus dB, but what have I lost? The connection between these two. Okay. The connection between these two, and that I lose twice. So, that is why 2. Am I clear? Okay. So, this is the gain which you have. Okay. So, take this example again. So, take this example and then what you can do at first step, you can have I take V2, V3, V6, V7 okay, and V1, V4, V5 and V8 and delta I. Okay. I have taken this as my first cut. So, the above is V2, V3, V6 and V7 and the lower one is V1, V4, V5, V8 okay, no problem. So, see this and now I calculate dA 5, 3, minus 1, minus 1, 3, 3, minus 1, minus 3. Okay, I am just not doing believe me. Okay. So, now what happens is, now you consider all the pairs, means n into n square pairs. You can consider n square pairs and from this n square pairs you can find which gives maximum gain. Gain means this one. Okay. And what you see is that when you consider 2 and 4, or I write it here 2 and 4, you get the maximum gain of 6.
So how did we calculate that?
This is DAs.
So do we have to take every pair and see
Yeah.
what's the gain and
Yeah. It is a NP complete problem. So, even heuristics cannot be very simple. Okay. So, no, 5 plus 3 and you see how many connections, 5 plus 3 8, 1 minus twice 1, 2 times 1, 2 times 1, so 6. Okay. So, this is the first, lock this, then go to the next one. Next one, just take the others and calculate. So, minus 1, minus 3, minus 1, minus 1 and this gives you minus 2. Lock them and see what happens if others, and so this is if you take this and this, then lock them. So, So, you can have the maximum gain or the least loss. Take the either the maximum gain or the least loss. Okay. And then you have minus 5, minus 1, minus 3, 3 and gives this 2 and minus 1. Okay. So, when this is given, see the largest sequence for which there is gain. So, largest sequence for which there is gain is this much, or you can also take this much.
What do you mean by locking?
Locking means when you are doing the next iteration, you are not considering those.
Means you have swapped those.
You have swapped those. You have swapped those and not letting it participate in the future swap.
Okay, so that it doesn't go back.
It does not go back. So, if you it will go back. Okay. Okay. So, this way you get 6.
So I didn't understand the last part. The longest sequence of gain.
So, if I take, so the what is the first thing is showing that swap V2 and V4. The second step, so you gain 6. After this swap V7 and what is this V5. Then you lose minus 2. Okay. Then swap, what do you swap? V8, then you gain again 2, and at the end if you swap V3 and V1, you lose minus 6. So, you will swap this, you will swap this, but most probably you can swap up till this 3. If you swap only this, you are gaining 6, but if you do this 3 steps, then also you are gaining 6. So, either you can swap once or you can swap thrice. So, at the end of this round, at the end you are getting the new configuration as V2, V3, V4, V3, V6, V7, V1, V2, V5, V8. Okay. So, okay. So, this is what we get. Okay. Iteration 1. So, go on doing this iteration. As long you get, so what is the gain in this iteration? 6. You will see in the next iteration the gain will be again 6. But if you go do the third iteration, you will have no gains. So, go on doing this iteration as long as you gain and stop when gain is found, and that is the final configuration. I think this is clear. So, we end our community identification algorithm here. Okay.